That's funny. That's a good idea.
Yeah, anyone else's car not warm up all the way, or is that well, 1.9?
Coming from Buffalo?
Well, no, I crash at my aunt's place.
Oh, okay.
20 minutes of driving, it doesn't even get up to town.
Yeah.
What year is it? It's an 02 Saturn.
Ooh, Saturn.
Yeah. It's freaking all over. Nothing in there.
I loved my Saturn.
It's what kind did you have? Cold of a thermostat in.
I forget the name of it, but it was just the SL, I guess. It was their like sort of base model, like a curvy little sedan kind of, you know.
No.
I got it because it was cheap, but it was a good car.
Just above a quarter of them. Wow. It's just what it does.
Huh. All right. So, does anybody have any homework questions you'd like me to go over?
You forgot to put any measurements on number 6.
Oh, okay. Did you choose some or?
Yeah, we all reversed it.
From there's a solution? Yeah. Okay. Sorry about that. Yeah. But other than that, any questions? You do need measurements, yeah.
Wasn't there something off on, what was it?
Is that the one that's like the X shape with the?
Yeah.
That's a cool problem with the pulley and stuff. Okay. Well,
Solution's even more cool because I don't understand where the numbers came from.
Yeah.
That's what makes it cool.
But no questions about the problem, just what I didn't give. Yeah, okay. Future generations of students will have those measurements given. Okay, so we were working on this from last time, so let's just finish this. So we had this thing where the angles were both 70 degrees. We had an applied 200 Newton force there. Each length was 2 meters. Each mass is 20 kilograms. And we want to calculate the internal loads. And when we calculated the external loads, if I call this A, B, and C, and I call this member 1 and member 2, yes, we got that RA is negative 135.70, 470.91, and then F12 is negative 64.29, negative 274.70, and RC is negative 64.29, negative 78.51. And the first internal loads calculation we did for member 1 with the coordinate system this way. And that means that you can think of it like this. Once that coordinate system and the long axis of the beam are aligned like this, it doesn't matter how you draw it. That's just how crooked you are looking at it, you know. And we calculated, so this was so going from the coordinate system. I guess I'll put this in parentheses because this is just how we're thinking about it. This is what's really going on is we're going to that coordinate system that's oriented with the member. And so to go from this to this is, yes.
After we rotated the axis, would you rather we cut like the left, or can we just leave it as the right?
To do the calculations,
Yeah.
I would draw it horizontal, but if you want to draw it crooked, you can, but I think it's easier to picture if you draw it horizontal. Just remember that what you're doing is rotating the coordinate system, not rotating the body. Want to hear something that's going to drive you crazy? Possibly for the rest of your engineering life. Half the people in the world rotate coordinate systems and half the people in the world rotate bodies. And so if you ever see in a book or a lecture or anything, rotation matrix that goes cosine theta, negative sine theta, cosine theta, that looks a lot like our rotation matrix, except where the negative is switched. This is the rotation matrix that rotates the body. But we do not do that here. So anyways, just be aware that that is a thing out there. Hopefully you won't have to encounter it, but you have to be clear on what you're rotating. Don't just think like, oh, I'm rotating and I use a rotation matrix. You know what I mean?
So is that functionally the same? You just like switch the sign up?
Yeah, it's totally the same. Yeah, because if you, so if we wanted to say that we're rotating the body from this to this, what we're doing in that case is rotating the body positive 70 degrees. Mm-hmm. And so then we have our rotation matrix is cosine of 70, negative sine of 70, sine of 70, cosine of 70. And that's equal to cosine of negative 70, sine of negative 70, just because of the even and oddness of the sine and cosine functions, negative sine. So those two things, if you think about them right, give you the exact same thing. You know, so if you're careful, you can use either one. If you're not careful, then 50% of the time you'll be right and 50% of the time you'll be wrong or whatever, you know. And that's not a very good goal to shoot for as an engineer, you know.
Engineer for blowing up rockets because one person used Imperium.
Yeah. Okay. So this was a rotation that's a clockwise rotation, so negative 70 degrees. And we did that calculation. And we got that T is equal to negative 92.18x plus 488.93. And V is equal to negative 33.55x plus 33.54. And M is negative 16.775 x squared plus 33.54 x. And if you, our body before we calculated those internal loads looked like this. So we had negative 135.71, 470.91. This thing down here that didn't end up coming into the internal loads calculation. But it's 135.71, negative 274.70. And then this distributed load for the weight is 98.1 newtons per meter. And after the rotation matrix, we got this thing that looked like, so we had negative 488.93, 33.54. I'll leave this stuff off. And then we add a horizontal distributed load component going this way of 92.18. And a vertical distributed load going down of 33.55. Okay, so let's look at the derivative relationships. dm dx is equal to v. dv dx has to be equal to the vertical q with some sign or the other. Now that we've switched to thinking of these in components, I don't know, you have to think through the signs a little bit. But anyways, you can see that in this case, dv dx, negative dv dx is equal to this downward distributed load. Okay, there's one more that we haven't talked about, and it's not really worth writing down or thinking about too much. But now, for the first time, we have internal tensions as a function of x. Okay, and so now, and because for the first time we have distributed loads in the x direction, and so now you can see that there's a derivative relationship between the internal tension and the distributed load horizontal component. See that? I guess in this case it's opposite, but yeah, negative dt dx in this case is equal to that horizontal distributed load. Okay, so now we're going to body 2. And this looks like, so after calculating the external loads, up at the top, we have negative 64.29, negative 78.51, and then at the bottom, 64.29, positive 274.70, and then a distributed load and let's switch this to a coordinate system just so we're all doing the same thing like this. Okay, so this time I'm going to just give you time to do every step just so you can check and make sure you're thinking about everything right. So take a minute or two and figure out what this rotation matrix is going to be. Let's just make sure we're all on the same page with the rotation matrix. So we're going from this coordinate system to this coordinate system, that's a counterclockwise rotation of 70 degrees, so theta is equal to positive 70. And so Q is equal to cosine of 70, sine of 70, negative sine of 70, cosine of 70. So that is 0.342, 0.940, negative 0.940, positive 0.342. Okay, so now go through. We really, like, if you're in a time pinch, there's no reason to do the transformation of the one up in the upper right, because that's not going to come up in the internal loads, but we might as well do it. So let's do the transformations now of these three loads and get ready to do those internal loads calculations. Okay, so this rotation matrix times the load at the lower left, 64.29, 274.70 is
that minus?
I don't think so.
Oh, no, I have that.
That should give you 280.12, 33.54. Yeah. Any questions on that? Then the distributed load, Q times, so this distributed load you have to represent as vector components. So that's going to be 0 for X, negative 98.1 for Y. And if you don't put that negative sign in there, you get most of the points on tests and stuff, but you get 0 points for the bridge that you make, you know. So negative 92.18, negative 33.55. And remember, this one is the distributed load, so I'll put newtons per meter. And then the last one, Q times negative 64.29, negative 78.51, and that gives you negative 95.76, positive 33.56. Okay, so now take a couple minutes and draw out a free body diagram of the whole thing with those distributed loads put. So now our final free body diagram of the whole thing. We have a force over here of 280.12, 33.54. At the other end, we have a force of negative 95.76, 33.56. And then for the horizontal distributed load, that's going in the negative x direction, so this way at 92.18. And then for the vertical component, that's going down, and the magnitude is 33.55 newtons per meter. Any questions about that? Anyone get anything different than that? Okay, well, how many cuts is this going to be? One. That's always the same answer for these when you're doing structures. Well, I guess it's possible if there was if there was an applied force that I gave you that was in the middle, then you might have two cuts, you know. But the distributed loads never change anywhere along the length. Okay, so now we have cut 1. And this cut 1 represents the whole thing, so this is 0 to 2. So now take a couple minutes and draw your the free body diagram of your cut with those distributed loads represented as point forces. Okay, so our cut looks like this. We still have the force over here of 280.12, 33.54. We haven't made it all the way over to the other external load, so over here on the right we just have the internal loads. And then we have our two distributed load components. The one going to the left at 92.18 and the one going down at 33.55. Okay, now the key step is going from this picture to the same free body diagram, but with those distributed load components represented as equipolant point loads. So do that. Okay, so it's the same free body. This point load is the same, 280.12, 33.54. The internal loads are the same. There's a horizontal point force now. Its location really doesn't matter because it's just acting straight along the long axis of the beam, and so it's not going to produce any moments. I'll put it at the center anyways. And that one is 92.18x. Everyone with me on that? And then the downward one is 33.55x. And now use this to calculate your internal load functions. So Newton's second law says 280.12, 33.54 plus negative 92.18x negative 33.55x plus T negative V is equal to zeros. And so the internal tension is 92.18x minus 280.12. And the internal shear force is negative 33.55x plus 33.54, that's round off error. And then the moment equation with the about point at the left. The horizontal distributed load is along the axis, so there's no moment for that. The vertical one is a clockwise moment, so that's negative x over 2 times 33.55x plus m minus v times x is equal to 0. So M is equal to positive 16.77 kind of thing. X squared.
Negative?
No, positive. That's just for, I'm just taking, yeah, I haven't added those together yet. It will be, yes, you're right. Minus 33.55 x squared plus 33.54 x. And so M is equal to negative 16.77 x squared plus 33.54 x. Okay. Any questions about that? Well, let's see what these look like. So for member 1, we got distributed loads of, so T equal to negative 92.18 x plus 488.93. V is equal to negative 33.55 x plus 33.54. And M is equal to negative 16.77 x squared plus 33.54. And then for member 2, we got positive 92.18 x minus 280.12. For V, we got 33.55 x minus 33.54. Nope, I did those backwards. So the first one is negative, the second one is positive. And then for M, we got the same thing as for member 1, negative 16.77 x squared plus 33.54. Okay, so for member 1, this is a linear function. We're starting at an internal tension of 488.93. And we're ending at 304.57. So the internal tension in member 1 looks like this. Okay, so the whole way it's positive. So is it in tension or compression?
Tension.
Tension, right? And then the other two are going to be exactly the same for both. So I guess I'll just draw that once. So for V, we're going to start at positive 33.54. and we're going to end at negative 33.54. So it's just a line like that. And for the bending moment, we're going to start at, this should be, I left the X off of both of these in those functions. So in both cases, they start at 0. In both cases, they end at 0. They go up to a maximum of 16.77. So like that. Okay, the shear force and bending moment are the same for both of them. So let's just draw the tension compression graph. This one starts at negative 280. And ends at negative 95.76. So is that second member in tension or compression? Yeah, this one's in compression the whole way. The magnitude of that compression is a lot less than the magnitude of the tension at every point. And so, basically, like the shear force and bending moment, you have to know more about this. We'd have to do a stress analysis to figure out where we're concerned about this being damaged. But you can see that you're a lot more concerned about the body on the left than you are about the body on the right because of those tension functions. It's funny because the problem looks so, I mean, it threw me off when I first looked at the external loads. It looks like such a symmetrical problem, but because we have pretty significant weights compared to the external loads, the weights are contributing to the problems of the one on the left, and they're subtracting from the problems on the one on the right. And so the net effect is that this one on the left is in a lot more danger of breaking than the one on the right. You know, that's the kind of thing we can start to see with these calculations. You know, we haven't had any way to do that before internal loads.
It
And
makes sense though if you look at it.
yeah,
Like if I were to like think about pulling on that thing
yeah,
and like imagine which one might break first, I
Yeah.
would definitely suspect the
yeah.
one.
Well, it's because of the weight. Because if those had negligible weight, everything would be symmetric with those. You would have a tension in the left member. So this is if you did the truss simplification. You'd have a pure tension in the left member and a pure compression in the right member that was exactly equal in magnitude. But because the weight comes in and makes things asymmetric, the one on the left is in more trouble. Any questions about that? Okay.
Joe's got a question.
Yeah.
Is there any time that instead of caring about how much force the 200 made, it was a displacement?
Oh, yeah. That's a great question. And we cannot do problems like that yet because we don't know. I mean, you can imagine. So we're trying to calculate forces, right? So now say that that point at B is displaced an inch, okay? An inch from its starting point. Well, if these are silly putty, that doesn't contribute much to forces. If it's steel, it contributes a ton to forces. You know what I mean? So intuitively, you know that we have to incorporate stuff about the material. And anyways, that fits into a category of problems called statically indeterminate structures, and we'll do that in D-form in the spring. Yeah, but that's a great question. In statics, we can't do anything like that, but in using the ideas of D-form, we can. Any other questions? Okay, that's all.